Climate change, nuclear war, asteroid impact, supervolcanoes, pandemics. All these constitute existential threats that could lead to the end of human civilization. Wide international cooperation could help avoid some of them, but certainly not others. Space exploration and the ultimate establishment of autonomous colonies in other planets is thus greatly necessary in order to ensure the survival of humankind. Advancements in space exploration have also proven to have multiple unexpected spin-offs, without which it is hard to imagine life on Earth as we currently know it. Atmospheric entry is one of the most challenging phases of space missions. Just recently, the European Space Agency's ExoMars mission failed while entering Mars, and we all remember the Columbia disaster that cost the lives of 7 astronauts after the shuttle collapsed during Earth re-entry. The extreme heat conditions that entry vehicles must withstand make the efficient design of thermal protection systems a very open problem. Multiple physical phenomena coexist and couple in complex ways, making it all the more difficult to model such environments and ultimately predict the flow behavior. Among them, the transitioning of the boundary layer from a laminar to a turbulent regime constitutes a potential mission killer. Laminar to turbulent transition is actually a fundamental process in fluid dynamics that one may observe in everyday tasks as simple as opening the water faucet. Opening it a little bit will provide a laminar flow, yet opening it further will lead to a turbulent water stream. This same process also occurs on atmospheric entry vehicles, and can lead to their catastrophic failure, since the turbulent heat loads can be up to 5 times the laminar ones. Moreover, during high-speed re-entries, the thermal decomposition of the heat shield significantly modifies the transitioning dynamics due to the modification of the surface roughness, the surface's porous characteristics, the surface temperature, and due to the injection of ablation subproducts through the wall.
Hi there, my name is Fernando Miró, and I recently completed my PhD at the Von Karman Institute and the Université Libre de Bruxelles. Within this frame, my doctoral research consisted in the development of simplified models for the transitioning of boundary layers in high-speed atmospheric entries, accounting for the thermal decomposition of the heat shield. Now, how did we do this? There exist multiple mathematical techniques to model the transitioning of boundary layers, and we can arrange them from more to less computationally expensive and also accurate. The top ones, so the most computationally expensive and accurate, are normally restricted to theoretical studies, whereas the last ones, so the least computationally expensive and accurate, are restricted to preliminary and rough vehicle design. Somewhere between these two worlds lie stability approaches. The main idea behind stability approaches is to start from a high-quality laminar baseflow, introduce into it a series of perturbations, and see how they develop. If perturbations grow, we say that the flow is unstable, whereas if perturbations damp out, we say that it is stable. Stability analyses therefore consists of 2 main steps. The first is the resolution of the laminar baseflow problem, and the second is the resolution of the perturbation problem. During my PhD, I worked on the development of simplified, state-of-the-art mathematical models for both of these problems, as well as on their implementation of such models into computational tools. The decaf flow solver was developed jointly with TU Delft and Texas A&M University in order to tackle the laminar baseflow problem, whilst the in-house Vesta toolkit developed at Von Karman Institute was significantly remodeled and extended to take care of the perturbation problem. In order to identify the individual contribution of the multiple coexisting physical phenomena in transitioning boundary layers around vehicles with a decomposing thermal protection system, a series of flow assumptions and boundary treatments were employed. The various flow assumptions featured various relations between the chemical and vibrational timescales and the flows. The tools developed are highly modular, thus providing the modeling freedom that is necessary for such a phenomenon identification and decoupling. Especially revolutionary in the field is the development of an automatic derivation and implementation tool for stability equations. This was done building upon the previous work carried out at the Von Karman Institute by Fabio Pina and Koen Groth. Novel tools were also developed for the automatic derivation and implementation of the thermodynamic derivatives of thermophysical gas properties with high-fidelity gas models. The combination of these capabilities provided a level of modeling complexity and freedom unequaled by any other research group in the world. These tools were then deployed on a series of test cases in order to address various research voids. How do baseflow inaccuracies propagate to the ultimate stability predictions? Can the E to the N method be applied to wall blowing scenarios?
Does the porous wall boundary condition developed by Gapanov and Fedorov for passive porous walls present a modeling improvement in scenarios with mass injection? What is the underlying reason for the advancement or delay of transition that was experimentally observed when injecting gases lighter or heavier than air? How do the boundary layer stability characteristics vary as a function of the surface porous arrangement? How sensitive are the predictions to the use of inaccurate transport, diffusion, collisional, or chemical models? What is the isolated effect of molar diffusion on the perturbation growth rates and frequencies? Which flow assumptions are valid at different trajectory points in an atmospheric entry? How do high enthalpy phenomena such as internal energy mode excitation, dissociation, ionization, shock perturbation coupling, or ablation product injection contribute to stabilizing or destabilizing the boundary layer? Are these effects mostly due to the modification of the base flow field or of the perturbations themselves? Which phenomenon is the one promoting supersonic modes in high enthalpy scenarios?
All this work resulted in 8 articles in top-level scientific journals, 6 of them as a first author, as well as 15 articles in international conferences. I am especially proud of the one we presented at the 2018 ICAS conference, which was awarded the Best Student Paper Prize from a total of 250 participants. Additionally, I also worked on the writing of a technical memorandum detailing the characteristics of the decaf flow solver, an open source tool which is now being used by several research groups in the world to tackle problems as varied as wind tunnel characterization and design or the resolution of subsonic wing flows. Additionally, the remodeling and extension of the VESTA toolkit has allowed for various doctoral students to build upon this work and perform state-of-the-art stability analyses.
Thanks to these and many other efforts, the community is advancing towards a better understanding of the potential mission killer that is the ablation transition problem in atmospheric entry missions. The resolution of such challenges will take humanity a step closer to the safe space exploration that is necessary to mitigate the multiple, imminent, and unpredictable existential threats that we face as a species.
Finally, I just wanted to take a second to thank the Belgian FNRS for funding all this work, as well as to everyone who, to a bigger or lesser extent, collaborated in this work. It would have been impossible without you. Thank you.